Okay, so 22.6, we're finally getting to what I consider some of the meat of this chapter, some of the most interesting ideas, and that is crystal field theory. And crystal field theory is a wonderful name. It has to do with predicting how the energy levels for the d orbitals in the metal cation are going to be affected by bonds formed with ligands. If you think about it, the ligands will bring in a new pair of electrons, they'll form a bond, and that creates some region of negative charge density. And so the d orbitals, which are also composed of electrons and negatively charged, are going to have their energies affected by that. They're mutually repulsive, right? They'll generally increase in energy because what you've done is you've forced two electrons now to get closer to those d electrons, and that mutual repulsion means that that will increase the energy. But what crystal field theory does is it looks at the geometries of the d orbitals. You probably haven't ever paid much attention to them. They're all just clover leaves. And then there's that one weird dumbbell with a hula hoop. And you haven't thought too much about it. But the fact that they are oriented, pointing different directions in three-dimensional space is going to really be important with crystal field theory. Now, these orbital energy level shiftings occur in ordinary covalent compounds as well, but we don't really care about it because most covalent compounds are going to have a completely filled valence shell of electrons. So every atom is going to satisfy the octet rule in a well-structured Lewis structure. And that means that there's no room for electrons to move around anyway. There are no vacant orbitals available. There are no unpaired electrons. And so there's not anything particularly interesting about how the energy levels in, say, carbon dioxide might shift when new covalent bonds are formed. But for these complex ions and coordination compounds, the D subshell of the metal cation is usually only partially filled, and so there are going to be vacancies, and the arrangement of the electrons within those orbitals within that D subshell is going to be really consequential and important. This is going to feel a little bit like molecular orbital theory when we've sort of finally analyze the results of the electronic structure. But anyway, so to start with, we just need to talk about crystal field theory itself, which says how the energy levels will shift. So ultimately we'll be able to predict electronic, magnetic, and spectroscopic properties of coordination compounds. So that's what we're going to build up to in the next section. So let's first consider a compound in octahedral geometry. So you see here on the right the metal cation with its 6 ligands arranged in an octahedral geometry. Then on the left you see the d orbitals, and they all have names. You again may have not paid too much attention to these, but the dz squared orbital is the one that's a dumbbell with a hula hoop. The dx squared minus y squared has its clover leaves pointed directly along the x and y axes. And then the dxy is pointing in between the x and y axes in the xy plane. And then the dxz and the dyz are also pointing in between axes in the xz plane or in the yz plane. So if you look at the octahedral arrangement of the ligands, the dxy, xz, and yz orbitals, those three on the bottom, are pointing more or less away from the ligands, in between them. And so the ligands are going to have a much less pronounced effect on the energy of those orbitals. But the dz squared is pointing straight up and down at 2 of the ligands. And then the dx squared minus y squared is pointed straight at the 4 other ligands. And so that's going to lead to more pronounced increase in the energy of those two orbitals. So let me move on to the next figure. Okay, so on the left you see how the d orbitals look before any ligands bond. They are degenerate. That means all 5 of them have precisely the same energy. They're just 5 different orbitals within the same energy level. But after the ligands attach, you see they'll all increase in energy a little bit. The xy, xz, and yz increase a small amount, and the z squared and the x squared minus y squared increases by a larger amount. And those form 2 new distinct energy levels. And they're called the EG and the T2G energy levels. Why they have those names, go ahead and take Chemistry 3620 to figure out what those letters mean. But anyway, those are the 2 new energy levels. And the difference between those energy levels is called the crystal field splitting. That's represented by that delta O. So that's the octahedral energy difference between those 2 energy levels. So that's how an octahedral complex energy levels will split. Now, the magnitude of that crystal field splitting is kind of on the order of the magnitude of energy cost that is required to pair electrons up. You may recall Hund's rule said that, let's say we're filling up a P subshell. Hold on, let me make sure that's not covered up, okay? And let's say this is like the 2p subshell for an oxygen atom. And so there are going to be 4 electrons in that oxygen atom. We're going to first go up, 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 and then we'll go down. That was Hund's rule, saying that we're going to spread them out first before we pair them up. And the reason is, these 2 electrons, they're both negatively charged and they're occupying the same region of space. And so there's an energy cost associated to putting 2 electrons in the same orbital. Well, if these orbitals have the same base energy as each other, then you might as well put electrons in empty orbitals first before you incur that energy cost of putting an electron in an orbital which is already occupied. Well, so if you have a small crystal field splitting energy, then it's actually less of an energetic cost to put an electron in the EG, in that higher energy level, than it is to pair any electrons. So if you have 6 electrons in a compound with a small crystal field splitting, then you will spread out all 5 electrons in each of the d orbitals before you then pair one up down in the T2G energy level. If you have a large crystal field splitting energy, then the energy cost for putting an electron in the upper energy level is greater than the cost for pairing them. And so you'll pair them first before you move on to the next energy level. And that's what we've been doing with all of our energy level diagrams up until now. So the one on the right is kind of the normal way to do things. The one on the left is where those energy levels are just so close together that we're going to treat them kind of like as if they're still a part of the same energy level and spread the electrons out. And so looking at that, the small crystal field splitting energies are going to have more electrons with similar spins. We have 5 upspin electrons and only 1 downspin electron. And so that's what we call a high spin complex, because the electron spins are going to add up. We'll have a total of a positive 4 spin instead of on the right side where they cancel each other out and you have a total spin of 0. So on the right side with the large crystal field splitting energies, that's a low spin complex. Low spin because the electrons are going to pair up more readily and the overall spin is more likely to be a small number or 0. Okay, so here figure 22.15 gives all of the different configurations for octahedral complexes. If you have 1, 2, or 3 d electrons, then it doesn't matter if you're high spin or low spin. But once you get that 4th electron, the high spin compounds are going to start adding electrons in the upper energy level. The low spin compounds are going to start pairing them up. And so for 4, 5, 6, and 7 electrons, you'll have a different electronic configuration depending on the magnitude of the crystal field splitting. And then back to 8, 9, and 10 electrons, it doesn't matter. They'll be the same either way. And we can kind of just zoom in on those 4 numbers where it matters, where you have a different configuration depending on whether it's high spin or low spin. Okay, and that is basically crystal field theory for octahedral complexes. So we'll go through the same thing with tetrahedral complexes and square planar. So in a tetrahedral complex, it's a little bit harder to kind of keep everything straight, but basically in this case it's the xy, the xz, and the yz that are more pointed toward the ligands and that are going to be higher in energy. The z squared and the x squared minus y squared are the ones that are sort of pointing between the ligands and minimizing the repulsive interactions with those new electrons forming the coordinate covalent bonds. So that means that the splitting of d orbitals in a tetrahedral complex will be kind of the reverse. You'll have 3 orbitals in the higher energy and 2 orbitals in the lower energy. So that's going to change exactly how the electrons are going to be distributed in high spin versus low spin complexes. Okay, 1 second. All right, and then lastly, we've got square planar complexes, and these ones are like the worst of all. So dx squared minus y squared is pointing directly toward all 4 ligands, and so that one is going to be the highest in energy. The dxy is pointing between them, but they all lie in that xy plane, and so that one's the next highest. The dz squared has most of the electron pointing up and down the z-axis, but there is that donut, which is just making the rounds in that xy plane and visiting each of the 4 ligands. And then the xz and the yz are largely pointing away from those ligands. And so the d orbitals are going to split in this fashion for square planar complexes. This is the last we're ever going to look at the square planar complexes. That it just gets a little bit complicated. Instead of having a single crystal field splitting energy, you have 3 different energy gaps, and each of them would have to be analyzed individually for whether it's high spin or low spin and things. So we'll actually leave this behind. All you need to know is that square planar geometries are complicated, and we'll never really talk about them again. Okay, so that's it for crystal field theory, section 22.6. We'll apply this and look at some properties of compounds that we can predict based on this theory in the next section.